Today we are going to be talking about invertible functions. As you'll remember in our last lesson, we talked about inverse functions, how you can find the inverse function, and how some functions, when you find the inverse turns out to not be a function. And so in particular, today we are going to be talking about inverses and those being functions, and how we can make something an invertible function. So we say a function is invertible if its inverse is a function. Now you'll remember that graphically this means that the graph will pass the horizontal line test. If a graph is not invertible, we can, let's call it like force it to be invertible by restricting the domain. So because you can tell that a certain graph, if you look at it using the horizontal line test, you can tell whether or not its inverse will be a function. And based on that, we can restrict the domain of that function so that when we find the inverse of it, it will be a function as well. Let's consider our most basic function that we were working with last time, whose inverse is not a function. So y equals x squared. So while it is not invertible, right, we know it doesn't pass the horizontal line test. We know that its inverse is not a function. We can make it invertible, or we can make it such that the inverse will be a function by restricting the domain. Right, so normally on its own, this is our graph y equals x squared. You can see it does not pass the horizontal line test, but if we restrict the domain to only part of that graph, we will be able to work with a function whose inverse is also a function. So for example, there are two different ways we can go about restricting the domain here. So one way is to just take the left side, so from 0 and less than 0, and only take that half of the graph. So if we restrict the domain to x being less than or equal to 0, you can see now that this would pass the horizontal line test, and therefore, because it would pass the horizontal line test, if we were to invert this, find the inverse of just this portion of the graph, we would be able to find that the inverse would also be a function. Another way to restrict the domain is to take the other side, the right-hand side, from 0 to all the positive numbers, and that would be restricting it to being x greater than or equal to 0. And again, in this case, graphically, you can see how this passes the horizontal line test, so you know that the inverse is going to pass the vertical line test, so the inverse will be a function. So when it comes to restricting the domain, a couple of things to help. First, you want to use the largest portion of the domain as possible. So you'll notice in the last example, the two different possibilities that I came up with, we got as far as we could without going too far. So we said, okay, let x be less than or equal to 0. But we could have said x has to be less than or equal to -2. Sure, that works, but it doesn't use the largest portion of the domain as you could. Now sometimes you'll be given a point that needs to be included. So for example, give the domain over which f of x equals x squared is invertible and contains the point 3, 9. So in that case, you know that in order to restrict the domain and include that point, we would have to use x has to be greater than or equal to 0. So here's an example. Determine if f of x equals x squared minus 4x is an invertible function. If it is not an invertible function, restrict the domain to make it invertible and contain the point 4, 0. Okay, let's start by thinking about what this graph looks like. F of x equals x squared minus 4x. Now, this is factorable, and if we were to factor it, it might help us be able to look at the graph because we would know exactly where we may have points on the graph. So x times x minus 4, once the x is factored out. And that means that we have zeros at 0, and at 4. And because this is a quadratic, we know this is going to be a parabola. And because it is a positive x squared, we know that this is going to be facing up. So this is the general shape of the graph. Now we need to restrict the domain to make it invertible. And we also want to contain the point 4, 0, which looks like is the right-hand side of this. Now our question is, well, how far do we go in order to get the largest part of the domain that we can? Well, we need to know where that vertex is. Now, there are a couple ways of finding the vertex. If you do have the rule, which we do, x squared minus 4x, you can use negative b over 2a to find the x-coordinate of the vertex, and then plug it back in to find the y-coordinate. So in this case, negative b would be positive 4 over 2 times a, 2 times 1, so 4 divided by 2, which is 2. Now another way to find the vertex is if you have the zeros already, which we do in this case at 0 and at 4, the vertex is going to be exactly halfway between those two. So halfway between 0 and 4 is 2. So we want to restrict it starting from 2 all the way to infinity. So x has to be greater than or equal to 2. And that's it. We've successfully restricted the domain. This yellow portion here that I've highlighted would pass the horizontal line test, which means that when inverted, it is going to be also a function as well.